Okay, so sorry about that. This is going to be part two now. All right, I'm still talking about 7-1. The next thing to talk about is fair and unbiased experiments. Like we were just talking about tossing coins. If you can be sure that the coin is going to end up equal amounts of times heads and tails, then that would be what we would call a fair or unbiased experiment. Now, all the stuff we're going to do is going to be fair. Like we might talk about dice that are loaded, or you know that a certain thing happens 60% of the time, so what's the probability it's going to happen 80% of the time if we do it twice, that kind of stuff. So just realize what those terms mean. Fair and unbiased means that it's got an equal chance of happening in any one of the possible outcomes that would go in that denominator. Relative frequency, I already talked about a little bit. Relative frequency was like when we were talking about the dice there in the calculator, when we ran the calculator simulation over and over again and talked about what was really going on. That's called relative frequency. And relative frequency comes up in two different contexts. If we weren't sure if I'm going to talk about two first, actually, because I was just talking about this. If we weren't sure if those dice were fair, one way you could do that is just roll it 1,000 times and see if you got equal numbers of 1s and 2s and 3s and 4s and 5s and 6s. Because if you did, you'd be pretty sure that it was fair. And of course, just like in our stats units, the more you do something, the more times you run an experiment, the more sure you can be that it's giving you an accurate representation of what's going to keep happening. The other way that relative frequency is used, and remember, relative frequency is about actual data collection. Relative frequency isn't a theoretical probability. It's about doing the experiment over and over again and making some tally marks and seeing what really happens. Sometimes probabilities are just so complicated to try to calculate that the best way to do it, you have to sort of resort to relative frequency. That's what number one's about here. That you just do the experiment thousands or millions of times, keep some data, and go, okay, look, 14% of the time such and such happened, and 31% of the time this other thing happened. So I don't know how this probability is actually being calculated. I don't know, what mathematical rules are really in place, but after doing this experiment enough, I can be pretty sure because of my historical data now that this is the probability it's going to keep happening. That's kind of how they do crazy stuff like weather and car accidents and things that are just got so many variables that are hard to control. They just start taking down some data and looking at, okay, this is how this thing's usually happening. Okay, so back to 7.2 now. 7.2 is about how do you count things when you've got more than one thing going on, or how can we count up possibilities, because we're going to be doing that a lot in probability. If the probability of things happening is always, it's always this fraction. Probability of an event happening is the number of ways it can happen that are favorable, sort of, divided by the total number of ways something can happen. It's a number of favorable ways divided by a number of total ways. So there's always a lot of counting going on here. First of all, when you're counting up sets, sometimes you don't just have one set. You're just trying to count that. That can be kind of easy. The first difficulty comes in then when you're trying to count up more than one thing, like two different sets of things. Like the example I keep using here is all the kids that are in FST, and you've got a set of kids that take FST at our school and a set of kids that take AP Psych. And we might want to talk about the union of those two sets, and you might want to talk about the intersection of those two sets. So I have these actually backwards here to kind of make you think a little bit. The symbol for union looks like the U, and I guess that's how you remember that. And the symbol for intersection, well, the word intersection kind of sounds like you're saying it. Intersection kind of sounds like a little N. Union, intersection. And that's what those symbols mean. If we were talking about the union of all the kids that take FST and AP Psych, union means we're bringing those sets together. Anybody who takes FST together with anybody who takes AP Psych. You don't have to take both those things to be in the union. You just have to take one or the other. So the word or shows up a lot with unions. I have that listed later in the document, but we could put that all here. Union means you belong in the union if you belong in any one of the requirements of the union. So the union is very inclusive. It's very easy to get to be part of the union. Whereas intersection is you have to be in all of the sets that are described. So if we're talking about the kids in AP Psych, that's a D. All the kids in AP Psych intersected with all the kids that are in FST. To be in the intersection, you have to be in both things. Kind of like when you think about intersections of roads. I don't have a lot of room to do it here, but you have two roads that meet together at an intersection. There's one road going sort of up and down, one road going sideways. The intersection is this part that belongs to both roads, that part that's in both. So the intersection of those two roads is those things in there that belong on both roads. It's sort of like the member of both roads. Any point in that square is part of both roads, so it's part of the intersection. I think it's a good way to think of intersection. Union is, of course, usually a large group of people, like union, like the United States. All the states of the union are part of the country, so it's you can be a citizen of California or Minnesota. You're part of the United States because you're part of the union. Okay. The next thing they talk about here then is this definition of mutually exclusive. If we're going to be counting up sets, we're going to be counting up multiple sets that go into this or go into this. You don't want to accidentally count incorrectly because that will change everything. It's a big deal in probability. So you got to be careful to know whether or not sets are mutually exclusive. Mutually exclusive just means that they don't have any overlap at all. You may have seen another way to describe this intersection and union thing. They talk about set A and set B like a Venn diagram. And if the two sets don't have any intersection at all, like, California and Minnesota, then if I wanted to count all the people in California and all the people in Minnesota, I could just add those two sets. It would be perfectly appropriate. But if I had sets A and B and they did have some sort of overlap, there were some people that were in both sets, like, I don't know, people who live in the central time zone and people who live in, what's a state that's not all in one time zone? I'm not sure. Like maybe Texas. I don't know if Texas is all in central time zone. So we had all the Texans and all the central time zone people. Well, there might be some people that are in both, and then it starts to get complicated. You don't want to count those people twice just because they sort of meet all the requirements of being in the intersection and in the union. So it starts to get to be kind of a mess. So mutually exclusive is an important thing. Mutually exclusive is when you have a situation like that where there's no overlap to worry about. Mutually exclusives are easy to add because all you got to do is add them up and you don't have anything to worry about. So that's kind of nice. We will hope to find lots of mutually exclusive. Well, if they don't, gosh, I got all this stuff in the way now. You can't really see what I'm doing. You can go back and look at that again if you want to see that. In probability, if you're going to add two things, here's the notation for that. If you're going to add two sets, we could add the union by just adding the things in one set plus the things in the other set. This means number of things in. This is what little n means in probability terms. The number of things in A or B, or in A union B, you can say it that way, is the number of things in A plus the number of things in B, if and only if they're mutually exclusive. Now here's how you write mutually exclusive. That their intersection is empty. That there is no element, the empty set here, there's no element that's in A and B, or in the intersection of A and B. There's nothing there. You can just add them up if they're not overlapping. This is the same thing but in probability terms. The probability of picking a random person in the United States who lives in California or Minnesota is just the probability someone's in California plus the probability they're in Minnesota, only if there's nobody that could ever be in both. And according to my definition, you can't be in both. Okay. I talked about this in terms of freshmen and sophomores. If we wanted to add up we wanted to count the total number of freshmen and sophomores, certainly you can't be a freshman and a sophomore. You would just be a freshman or you'd be a sophomore. There's nobody who's both. So all you would have to do, so for your answer for question 6 here, all you have to do is to find the probability or to find the number of people. I said probability, didn't I? Find the probability that you are a freshman or a sophomore, or the probability that you're in the union of freshmen and sophomores. All you got to do is count up the probability that you're a freshman plus the probability that you're a sophomore, because that won't inappropriately double count anybody, because you can't be in both. Why won't that work for I'll get that question back here. Why won't that work for FST and AP Psych? Well, the thing is with freshmen and sophomores, you got the freshmen and you got the sophomores. You add this probability with this probability, you haven't double counted anybody. If you have FST and you have AP Psych, there's a problem here, because there's some people in here you won't want to count when you count up this thing and then you try to tack this on. That's gonna be a problem. You can't just add that up, because there's some people you've counted too much, and they are inappropriately making your union look bigger. So how do we account for that? Well, if I counted all the people in FST, and then then I add up all the people that count for AP Psych, I will have counted these people in the middle twice. If I know how big this area is, I can do, or how many people are in here. If I subtract them once, I'll have the total number. I'll have sort of 3 discrete sets here. I'll have all the people in FST, plus all the people in AP Psych. Well, of course, I would have counted these people twice. So if I subtract this number one time, then I've just got them counted once in the whole set. So let's pretend we had some actual numbers here. Let's say that the total number of people in FST is 130 people in FST. and that there's 50 students in AP Psych, but I know that in this area that there's 20. So in here, you can kind of think of how, okay, there's 130 people total in here, but 20 of them are in this area. And I've got 50 people total in here, but there's 20 in this area. So one way, the formula says, I take 130 plus the 150, that gives me 180, and I subtract out 20. Is there another way to do that? Is there a way we could write that and just sort of check our answer to make sure this is, I'll call that FST and A for AP Psych. If I know there's 130 total in here, and there's 20 of them in this area, I'll put the 20 here, that's good, yes. Then you can think of how many people will be out here who are not in AP Psych. Well, that should be 110, right, to make 130 total. And if this is 50 total, and there's 20 already spoken for now, there would be 30 in here. And now, another way to think about this is now I really do have three completely mutually exclusive sets. Like you can't be in this number and be in this number because I've separated them out. This is the people who are only in FST and not AP Psych. These are the people who are only AP Psych, not in FST. And then these are the people who are in both. So by defining them that way, now they look like they should be appropriate to add. And guess what? 110 plus 20 plus 30 happens to be the same number I've been looking for. Another way to do that, even still, is to go, okay, just think about this 130, and let's just add on the people who are in AP Psych that I haven't already counted, and that's 30 new people because they weren't counted in the FST number. Anyway, so there's two different ways you can answer number 7. One I wrote, the other one I just talked about. Yeah, here they say how to do that in probability terms. If I want to find the probability of the union, I can add up the two separate probabilities, but then I have to be careful. I need to subtract off the intersection because I don't want to count them twice. If I subtract them once, then I will arrive at the correct total. So I put in some numbers here, and I actually calculated some probabilities, and you can see these as numbers between 0 and 1. Realize, if I haven't said this yet, that probabilities are always going to go between 0 and 1. If the probability turns out to be 0, and none of these are 0, but if the probability turns out to be 0, like what's the probability that someone in our school is taking, I don't know, what's a class we don't offer? Probability that a student is taking German. I don't think we offer German at the school. Probability that the student is German is 0 because there's no German. What's the probability that the student is, I don't know, living in Singapore? That would probably be everybody. So the probability that the student lives in Singapore at our school would be a probability of 1 because everybody does. And probabilities will always range between 0 is totally ridiculous and 1, which means there's no way around it, it's got to happen. And because of that, here's this last statement here. Since probabilities always add up to 1 when you count up everything, like what's the probability that someone lives in Singapore and what's the probability that someone doesn't live in Singapore? Those things should add up to 1 because either you live in Singapore or you don't, and that counts for everyone in the entire world. So if, say we knew the probability that someone on the planet lived in Singapore, and say we knew that was, I don't know, 1%. It's probably not even that big. But then the probability that someone lives outside of Singapore would then be 99% because I need those two things to add up to 1. To find the 99%, I would just take 1 minus 1%, and that would give me the 99%. Thank you for watching.